All right, so here we go with part 4. Part 4 of 9.3. All right, so in our previous couple of videos, we were looking at finding a probability or an area for a normally distributed random variable. So we were taking x's and turning them into probabilities. In this section, we're going to do that backwards because that's what happens in math. We actually turn x's into y's, and we do that for a while, and we suddenly say, hey, turn that y back into an x. So we were turning x's into probabilities. Now we're going to turn probabilities and find that x. What that means is we're going to be asked questions like this one. Find the z-score that corresponds to a cumulative area of 0.3632. All right. So I see in the problem that my job is to find a z-score, so that means I'm working with a z-score. That means that my mean is 0 and my standard deviation is 1. Okay. My area is 0.3632. What's that z value right there? What is that z-score that makes that happen? Well, I'm going to use technology and find this. So I'm going to go to my calculator. I'm going to go back to that same distribution menu, but this time I'm going to use a different command. I'm going to use the inverse normal command. And the inverse normal command answers this left tail problem. So I'll punch that up. It's going to ask me for the area. The area is 0.3632. It's going to ask me for the mean of my distribution. And since we're doing a z-score distribution, that's going to be 0. My standard deviation is 1. I'm going to paste that back in, and I get that z-score right there is negative 0.3499. And there's my z-score. Okay. If you happen to be using an 83, the command is inverse norm, area, comma, mean, comma, standard deviation. Right? Now there's one difficulty here, is this only works on ones that look like this. This command is only for left tail problems. If your problem is anything other than a left tail problem, you can't do it. Well, that's a lie. You can do it, but only if you can find a way to rewrite it as a left tail problem. Here's what I mean by that. Find the z-score that has 10.75% of the distribution to the right of it. Z-score. That means my mean is 0. It means my standard deviation is 1. The middle right here, that's going to be our 0. I'm asked to find some value over here where this piece to the right of it, is 10.75% or 0.1075. I can't do that because my command only gives me left tail. But what I can do is I can find this left tail, where the left tail is just going to be 1 minus 0.1075, or what is that, 8925. So then I'll grab my calculator, and I'll say distribution, inverse normal, area to the left is 0.8925, mean is 0, standard is 1, paste, and I find that that has a z-score right there of 1.24, round to 2 decimal places or round wherever they want me to round it. Okay. So my job in Chapter 9, Section 3 is to take a look at exploring the idea of a normal distribution and using that normal distribution to find probabilities. Right? Now, most of the time, we're just going to find probabilities or ranges of values, and it's just going to be plugging it into the calculator and grinding it out. Every once in a while, this idea of the z-score is going to show back up. Right? Now, I've been using a lot of z-score examples in here because they make this easy. The mean is 0, standard deviation is 1. Mean is 0, standard deviation is 1. I don't have to type it out every time. Right? But most of the real problems are going to be like these guys right here, where there are just some normal distribution with some random mean and some random standard deviation, a random mean and a random standard deviation, and some questions about ranges of values. Right? Occasionally, though, if you have a z-score and you want to turn it back into an x, you might need a formula for it. And here's the formula. Now, technically, this isn't a new formula because we had the z formula from earlier. We used it once. We said z was equal to x minus the mean divided by sigma. And if I wanted to, could I use some algebra and solve that for x? And if I solve that for x, I would just get this. Okay. All right, let's take a look at a couple examples and then try to figure out where we'd ever want to use that. A veterinarian records the weights of cats treated at a clinic. The weights are normally distributed like that. Okay, with a mean of 9. Okay, so I know that my mean is 9, and a standard deviation of 2. Standard deviation of 2. Find the x's, the weights, corresponding to each of the following z-scores, and interpret. So what would it mean if I had a z-score of 1.96? Right? What does that mean for a cat? All right, well, let's see. Let's turn that z-score into an x. The x would be the mean plus the z times the standard deviation. So I'm going to grab my calculator. 9 plus 1.96 times 2 means 13 pounds, roughly. 12.92 pounds. So a z-score of 1.96 means a mean of roughly 13 pounds, or that's a big cat. How about a z of negative 0.44? Well, a z of negative 0.44, what would that be in terms of a cat? Well, mean plus z-score times standard deviation. Grab my calculator. 9 plus negative 0.44 times 2, 8.12. Or a lightweight cat. It's below average. Average was 9. The last one they want us to do is, what would a z of 0 mean? If z is 0, what does that mean in terms of x? Well, mean plus z times 9. So a z of 0 means the mean. So if you have a z of 0, if z-score of 0 means you're decidedly average, completely average in every way, shape, and form. All right, so let's take a look at how problems on the exam might show up, and here's what they're going to look like. All right, these are the problems from the exam. We'll start here. Right. All right, so let's read this first one so we can make some sense out of it. Scores for the California Peace Officer Standards and Training Tests are normally distributed with a mean of 50 and a standard deviation of 10. An agency will only hire applicants with scores in the top 10%. What is the lowest score you can earn and still be eligible to be hired by the agency? Okay, I've got normally distributed. I've got a mean of 50, and I got a standard deviation of 10. So I'm just going to go ahead and draw that picture. Okay, that middle right there, that's my mean. My mean is 50. My standard deviation is 10. Okay. And an agency will only hire applicants with scores in the top 10%. So there's some score over here that if you score high enough, this area right there is only going to be 10%. And we want to know what's that number right there. How high of a score do I have to get into that top 10%? Well, that looks like one of those inverse normal problems, but the challenge is I can't actually do that one because that's a right tail test. The only thing I can do is a left tail test. Okay. So I'm going to turn this right tail test into a left tail test by saying that if the right is 10%, then the left must be 90%. And then I'm going to grab my calculator. I'm going to use that inverse normal command. And I'm going to say the area is 0.9. My mean is 50. My standard deviation is 10. And that score is going to be that X value right there is going to be a 60, sorry, got ahead of myself, 62.82. Okay. Now, since the mean and the standard deviation are both given to me as whole numbers, I'm going to round that and call that 63. You'll notice I rounded up. I know I'm supposed to round up here, but also I want to make sure that I round into the region that I want rather than rounding down, okay, because I want to make sure that I score high enough that I'm in the top 10%. So the lowest score to get hired is a 63. Okay. All right. In a randomly selected sample of 8 women ages 20 to 34, the mean total cholesterol level is 170 milligrams per deciliter with a standard deviation of 38.9 milligrams per deciliter. Assume the total cholesterol levels are normally distributed. Okay, I'm just going to stop right there because I'm liking what I'm reading. Normally distributed, mean of some number, standard deviation of some other number. So I'm going to go ahead and draw that picture. There's my standard normal curve. Okay. I have a mean of 179. I have a standard deviation of 38.9. Okay. Okay, what do they want me to do? They want me to find the highest total cholesterol level women in this category and still be in the bottom 1%. I want the highest and the bottom 1%. So that means they want some number over here so that right there is 1%. Now, clearly this is not to scale, but you get the idea. Okay? Is that a left tail or a right tail? Well, that looks like a left tail they want me to work with, and I can do that. I can just use that inverse normal command. So I'm going to grab my calculator. I'm going to go to my distribution menu. I'm using that inverse normal command. The area that I want is 0.01, 1%. My mean is 179. My standard deviation is 38.9. Paste that back in, and I get that is an 88.5. So the highest possible total cholesterol that someone could have and still be in that bottom 1% is an 88.5. So the highest total cholesterol level is 88.5, and these are what, milligrams per deciliter to be in, what is it, the bottom? Yeah, the bottom 1%. Okay, well, that wasn't too bad. Okay. All right, assume the salaries of elementary school teachers in Arizona are normally distributed with a mean of 34,068 and a standard deviation of 33,435. What is the cutoff salary for teachers in the top 10%? Well, let's see. I was told they're normally distributed. I'm told that they have a mean. I'm told we have a standard deviation. So I'm going to go ahead and draw that picture. My mean is there. My mean is 34,068. My standard deviation is 3,435. I want to cut off for the, so this is like the California police officers one. There's some number over here where this is 10%. And I want to know, what is that salary? What's that value right there that gives me that top 10%? I can't do that, but I can do this. I can do that right tail turned into a left tail version of this. And so then this over here is going to be what, 90%? So then I'll bring up my calculator. Again, I'm using that distribution menu and inverse normal. I'm told the area is 0.9. My mean is 34,068. My standard deviation is 3,435. I'm going to paste that back in, and I get that they must make a salary of 34,470. So the cutoff salary for the top 10% is $38,470.13. Now, I don't know if we need to go this accurate or not. Maybe they'd be okay with just $34,470, but I got it, I'll do it. Okay. So I'm finding these values, just grinding them out. All right. Assume that the heights of men are normally distributed. Ooh, I like that already. Normally distributed with a mean of 70.7 and a standard deviation of 1.1. Okay, so I'm just going to go ahead and draw that picture to begin with. Normally distributed with a mean of 70.7 and a standard deviation of 1.1. If the top 5% and the bottom 5% are excluded for an experiment, what are the cutoff heights to be eligible? Oh, round your answers to 1 decimal place. All right, so we need to cut off people on both ends. We need to cut off 5% here and 5% there. So as for whatever reason, we have an experiment where we don't want short people and we don't want tall people. We just want people in the middle. So I need to find out what are those values to cut that off. Like, what is that number and what is that number? Well, this one looks like a left tail test, and so I can just do that. This one looks like a right tail. I can't do that, so I have to turn that right tail into a left tail. So I'm going to bring up my calculator. The first thing I'll do is I'll find that left tail one that I know over there. I'm going to find this one on the left. That's an inverse normal. The area is 0.05. That's that 5%. The mean is 70.7. The standard deviation is 1.1. And that gives me a 68.9. And these are inches. So you must be taller than 68.9 inches. And now I need to figure out the other one. So it's the same command again, inverse normal. But now the area is 0.95. Do you see why it's 0.95? 5% to the right means 95 to the left. And that means over here is a 72.5 inches. And so if you want to be in this experiment, you have to be between 68.9 inches and 72.5 inches tall. You're taller than that or shorter than that, you're out. So what is this, roughly 5 foot 8.9 inches. And this is 6 foot 0.5 inches. If you're taller than 6.5 inches, or you're shorter than 5 and 8.9 inches tall, you can't be in this experiment. But 90% of the people can be in this experiment. Okay? And if 90% can, 10% can't. Do you see how the two tails add up to 10? Okay. That brings us to the end of section 9.3. We'll come back and do section 9.4 here in a minute.